Okay, our second speaker today is Simon Davidman from Imperas Software, where he's president and CEO and initiator of open virtual platforms. He has been working on simulators and EDA products since 1978. Prior to founding Imperas, Simon founded Co-Design Automation, the developer of SystemVerilog, and also an executive of the European GM with 5 EDA startups, including Chronologic and Ambit. He's based in the UK, and the title of his talk is Generation and Configuration of Functional Coverage and Verification IP for RISC-V Processor Verification. Okay, thank you, Simon.
Yeah, hi. Can you see my screen all right, Mike?
Yes.
Yeah, go ahead. We can see it.
Okay, yeah. Well, great. Well, thanks very much for the opportunity. And I mean, yes, you're right. I've done a variety of different interesting things in my past, but actually the thing that's really exciting for me at the moment is verification of processes around RISC-V. And that's what I'm going to talk about today, is automating as much of this as we can in here. And in terms of the agenda, I'm going to talk, just briefly introduce why I think everyone's getting into the RISC-V world, and then talk about some of the challenges that it brings with it, and then get into functional coverage and the automation of that, and then go through an example. RISC-V, why RISC-V and why now? I mean, because pretty much every design that we come across as an EDA company, people have been working, have embedded processes in it. And that's really because most electronic products now are being defined by their software requirements, which means there's lots of processes inside them. And, you know, that sort of started, I don't know, probably 10, 12, 15 years ago. And obviously at that point, there were several different ISAs being used, and pretty much every chip had some small microcontrollers or larger applications. And products are being defined now more and more by the software requirements in them. And there are existing challenges with the existing ISAs. You know, companies like MIPS have gone away. ARM's changing its business model, but wildly successful. And people are trying to find better ways to get things done. And there's a lot of initiatives to do with collaboration, to bring down the cost, timescales, and to help. And there's a lot of going on, especially in the RISC-V world, around open source. And so there's a time and place, and for RISC-V it is now in there. And what makes it so attractive is not the fact that it's open or standard or anything. That's part of it. But what we see is that the key thing is that it's freedom. It gives the designers freedom to do what they need, to develop their own processes and to configure it and extend it. So it allows them to do things they could not do before. And with these freedoms comes a cost. And one thing that's really important is to have something as a very standard executable reference in there. So you need a very highly capable model of it. And there are several sort of bullet points. You know, I could go on for days talking about what models need, but you know, it needs to be complete, it's got to be fully verified, and a lot of people need to use it. It needs to be able to be controllable and analyzable so you can embed it inside other environments. Needs to have methodologies for RISC-V, especially so it can be extended and configured. And then when you have this model, you've got to be able to use it with industry solutions. No one wants something that works just in isolation. They want it to work with the tools that they're using, whether it's the virtual prototyping technology from Synopsys with Virtualizer, or whether it's the verification solutions with the SystemVerilog simulators. Whatever reference model you're going to have for your processor, it's got to work with these. And then it's got to have, you know, it's got to be extremely fast, because people have billions of lines of software they want to be trying to run through this. And it's got to have a low memory footprint. If you want to run 1,000 processors, it's got to be high capacity. So there's a lot of requirements on the model. And on top of that, there needs sophisticated tooling for simulation for the software developers, that they require basic virtual platforms which include these models. And then there needs to be a lot of verification. I talked at the RISC-V Summit a year ago, December last year actually now, talking about verification there. And you know, we dug up some information on the ARM process where they talk about 10 to the 15 instruction cycles that they have to validate for a high-end application for. And if you put that in context, you know, it's 15,000 years of a simulator or 30 years of an emulator. And this is why people building high-end processors have tremendous verification environments with a lot of verification technology in it. And more and more people in the RISC-V world are going to find that they need to do more verification. Maybe they don't need to do the high-end application processors, but they're going to be doing custom instructions and things. So there's a lot of cost to these, the freedoms that RISC-V brings. And now, from an Imperas point of view, we've been building sort of fast processor models actually for quite a while. We started off with the MIPS and ARM and people like that. And now in 2016, we've started doing RISC-V, and we're using our technology has been used for architecture exploration, software development, and also DV. And now I'm just going to skip these, a lot of these model slides, go quite quickly here, but basically you need a base model which implements the specification. And from an Imperas point of view, we use these open virtual platforms, APIs, which are an open standard. And we've done some 15 different ISAs, and there's about, I think 22, 23 have been done with them. And the key part of our technology is the model is separate from the simulator. And the models are very configurable, and you can extend them. So we provide models of a lot of different processor IP vendors' cores, where we've specifically configured it with them and they've extended it. And then users can then take it further and add their own instructions and CSRs. And that's, again, this beauty of RISC-V. You can license a core and then you can extend it. And those can be either proprietary or open source. And when you've got this model and you've extended it and you've got it working, from an Imperas point of view, we can run it in a verification environment. I'm going to talk more about that in a minute. And we can also run it in a virtual platform environment where we're running it in a sort of a test bench, and we can run full operating systems, and there's all software development tools. But I'm going to focus more on the verification here and the challenges, and get into the functional coverage of it. This is a DV group, so I don't really need to go through this. You got to have a verification plan. You got to have functional coverage as a key part of that to measure where you've done using SystemVerilog in there. Now, when it comes to a processor, that's something that's traditionally not been done outside a few large companies, but now everybody is having to do processor DV there. And there's really two parts to it. There's the stuff which is the standard ISA stuff, and the stuff which is customer specific in there. So the standard ISA is going to be the same for everybody, and so that should be developed collaboratively and made available, and there should be tools that do it. And then the custom ones, people are going to have to do themselves. But one of the key things you're going to need is functional coverage. And if we look at the standard ISA, and actually this slide is now a little bit old, but if you look at the basic instruction sets, we're actually over 1,000 instructions now for the different extensions that are part of RISC-V. And each one of them is going to need SystemVerilog. So you're into the hundreds of thousands of lines of code, and it's not specific to your core. That's the key thing. And if you've got to write it by hand, it's pretty tedious and error prone. You need it for each design, but it's unnecessary really to redevelop it. So there needs to be some form of automation and collaboration. And that's really what we've been doing with what we call RISC-V ISACOV, which is basically to try and develop with input from partners automation to get this functional coverage done. And so I'm going to talk a little bit about that. And so this is what we're talking about with RISC-V ISACOV. This is SystemVerilog functional coverage. And the key thing is the RISC-V definition that we have, so we can automatically generate the coverage from it. And there's a lot of coverage groups, and it uses a standard trace format to come from the core into the functional coverage. And this is how verification is measured. Now, what I'm going to do now is to talk about a case study with the open source CVW core that comes from the, actually that's not, you're not going to want one like that. You're going to want me to only talk when the slide's up, right? Okay, so it measures how much verification is done. Now I'm going to talk about a case study with an open source core from the Open Hardware Group. This core was developed by Harvey Mudd College, Oklahoma State University, and University of Nevada with Open Hardware, and it's a 5-stage core. And one of the interesting things is it's the basis of a book on processor design, which is coming out next year. And prior to working with Imperas, the RTL was running the compatibility tests, it was running their own tests, it was getting code coverage on the source up to 90%, so it's pretty good. And the methodology was running a sort of signature compare, where information was dumped to a file from a run with the RTL and with simulation and compared, and the RTL was successfully booting Linux 500 million instructions in SystemVerilog and on an FPGA, which is all very good. But in terms of completeness, when we measured it with RISC-V-ISACOV, actually it only covered 38% of the different coverage groups we got for instructions, very low percentage, 2% of the cover points and bins, and actually for virtual memory, MMU, only 11% of the coverage. So Linux is not a very good verification solution. And what we did is we also took the core, put it in a test bench, and ran it with the Imperas DV product, Imperas DV, which includes the reference model and connects to the ISACOV and connects to the core with a trace. And we used the Chips Alliance, which came from Google Random Generator, RISC-V DV, to generate random tests for it. And you basically run the test on the RTL, and on every event, you do continuous compare with the reference model in the Imperas DV technology, and it gives you the mismatches are reported immediately, and also it can handle asynchronous and events and everything. So it's a complete verification solution for comparing. And when we ran that, we immediately found there were issues and bugs, and we recently added more tests, and we found more bugs in the virtual memory side of things. You've got to really look into your verification environment to say, well, how should you be doing it? Should it be post-simulation trace compare or signature compare? But those aren't really good enough. Booting Linux really isn't good enough. You really need a good processor model, and you need a good methodology, which includes things like functional coverage, and you need to have automation to get the job done very quickly in here. And as was talked about by the previous speaker, automation is going to be needed more and more in helping build the DV environments that we've got going on. So sort of in summary, you've got to generate verification components because it can really help you get to a quality sooner. And if it's based around, as what we're doing here, the RISC-V ISA, we can have machine readable formats which can be input to these generators, and that can be standard. And we've created some of this technology based around some work we did in the open hardware group with the collaboration there with commercial users, and it's been in use in 3 different generations, and we're working on more things there. And so really, just to wrap up, RISC-V Freedom allows people to build these domain-specific processors, but it's not free because there's a lot of work that you need to do in terms of verification and tooling and technology in there. But it does give you the ability to do custom implementations for your own specific job, but you need to build models of that and verify that. And one of the things that you've got to remember is that verification is an exponential, endless problem here. And you have to balance the cost of finding bugs with the cost of not finding the bugs here. And we're a great believer in automation, and our latest technology here, the RISC-V ISACOV, that's been used over the last few years, is really helping to build these DV environment to get people to the market sooner. Thank you. Back to you, Mike.
Okay, thank you, Simon. Just coming off mute. I think we're bang on time there, so we don't have any time for questions. If there are any questions, we'll send them to you separately. But thank you very much, Simon.
Thanks very much.
Thank you.